Yeah, so today I'm going to be talking to you about real-time airborne magnetic navigation with MagNav.jl. So we've been coming to JuliaCon for the past 3 or 4 years now, presenting sort of the same subset of software and some data collections we've done over the last few years. This is kind of bringing that all up together and wrapping it up with a nice bow for what we've been trying to do for the last several years. I'm pretty much going to start with what is MagNav, because we've kind of realized it's a niche topic and a niche topic because most people don't work in navigation and most people specifically don't work in alternative navigation. Then we'll go through some of the data we've got as well as sort of the approaches that we've been taking. So the core problem we're addressing is GPS denial. As I'm certain most folks here are probably more keenly aware of than back in the States, GPS is kind of trivial to deny, be it any kind of GNSS system. You're kind of seeing this acutely through commercial airfare in Estonia and Finland right now, as well as in the entire Ukraine. It's kind of a very vulnerable technology, and this is sort of also true for BiDAO and the other sort of GNSS systems. However, you do kind of need GNSS to correct any kind of inertial system, which is what you're using moment to moment to navigate. It acts as a way to ensure that your inertial navigation system isn't drifting off into oblivion and assuming that you're in the middle of the ocean when you haven't left Germany yet. There's a lot of other ways of doing this. You could do terrain following, which works great if you have a good map. Visual navigation, which works great if you're doing SLAM and going to be over the same area for quite a while. Signals of opportunity, so if you know what signals are in the area, like Wi-Fi is a great way to do this. You can generally just position off of that. And then celestial navigation, which we've been doing for, I don't know, a couple of millennia, just looking at the stars and trying to figure out what's going on. Each of those, though, have some cases where they're great and a lot of cases where they're awful. Some great examples are like visual navigation when it's cloudy and dark. I don't know what you're looking at. So we're looking at MagNav, which is using the Earth's magnetic field, or more specifically, the crustal magnetic anomaly field to navigate. So you're looking at the distributions of ores and other objects within the Earth's crust and measuring the magnetic field due to those components to try and navigate. This is something that's been well explored in sort of the oil and gas industry, because this is the same fundamental process you use if you're, say, doing a geosurvey to try and find oil or natural gas deposits over an area. You effectively have to build the map that we're using in order to find those deposits. Additionally, since magnetic signals, unlike electrical signals, degrade with 1/r², it's kind of difficult to jam this. We did some back-of-the-napkin power calculations at one point, and you kind of have to put a nuclear reactor on a train and follow your plane around to have any kind of perceivable impact on what you're measuring at 30,000 feet or mid-flight. So diving a bit into the magnetic field, I mentioned the core anomaly field, or the crustal anomaly field. That's really just the components due to things like the lithosphere and the mantle, so sort of the upper mantle or the crust regions of the Earth. You do also measure the Earth's core field, which is very well modeled, and the Earth's space weather effects, so what's going on with the sun and other things, which isn't well modeled, but you can normally get around by having a base station somewhere and just measuring the differential off of that. The last thing, and sort of the most important thing from a deployed perspective, is the platform effects. So if you actually break things out by magnitude, the core field is somewhere in the neighborhood of like 30 to 50,000 nanoteslas day to day. So tens of thousands of nanoteslas. Temporal variations or space weather effects are somewhere in the area of like 10. We don't really care about 10 nanoteslas, because the crustal anomaly field, or what we're actually using to navigate, is on the order of about 100 nanoteslas of variation. So if you're off by 10, even if you're off by as much as like 30 or 40, you're normally okay, assuming there's still sufficient variation. And then with the platform effects, you kind of end up with a couple of very different cases. If you're on a geosurvey aircraft and you've put your magnetometer on a 3 to 5 meter long boom behind the plane, you're only detecting up to about 10 nanoteslas from the aircraft, which we could ignore. I can't put a 5 meter long boom on an F-16 or on a Boeing 737, well, I mean, that might crash, or on any other kind of commercial airliner. So for those cases, I have to put in the actual cockpit or the cabin itself, and there I've personally seen as high as about 3,000 nanoteslas of variation in the signal, at which point you have completely lost the anomaly field in the noise. This means that we actually have to do something called platform calibration, and the conventional way of doing this is something called Tolles-Lawson. So 1937 and 1942, a couple of folks, Tolles and Lawson, came up with some approaches for doing this on sort of World War II era aircraft. because they were trying to figure out how do you navigate across the ocean. And they're like, well, the magnetic field could be kind of useful for this. As it turns out, they weren't able to put the maps together, so that kind of got binned. And then in 55, they wrote out their equation. And it's really just a quick way of saying, if we look at the aircraft in multiple orientations to the Earth's field, what do we see as far as its magnetic field? Once you have that, if you know your orientation, you then know a couple of the components of your magnetic field and can subtract that off your signal. This doesn't get everything. This is perfect for a geosurvey aircraft. And realistically, with a geosurvey aircraft, you're done at this point. For a jet, there's so many other temporal things that aren't quantified here, like varying electrical signals, lights, the fuel pump, passengers, that you have to do something in addition to this, which is sort of where the rest of our project comes in, and I'll get to that in a second. But if we sort of take a step back and look at what the ConOps looks like, or what the actual application space looks like here, you start with GPS. So we know where we started. We lose GPS at some point, and we continue using INS to navigate. And then while doing that, we measure the Earth's magnetic field, remove the platform effects, and use that to bound where our INS can be stepping to. So we're not eliminating error. We're simply saying the error in the INS will never exceed this value. We're dampening the growth in error to near zero. So taking a high-quality INS, damp it to near zero, you can pretty much navigate on that forever in a 50 to 100 meter bubble, and no one's going to care. We don't always need the 1 to 5 meters that GPS guarantees us. So it works. We know it works. We've done it a bunch on a geosurvey aircraft. Like I said, though, this isn't helpful. Sure, it works when everything's on a stick, but we kind of have to figure out what it looks like when we actually go on a plane and put it somewhere else. So to pursue this, we put together a data set where we kitted up a Cessna Globemaster with an additional 4 or 5 magnetometers within the cockpit, some additional voltage sensors, some additional current sensors, just sort of anything we figured could come up with a magnetic signal. We kitted it up with a sensor to see if we could detect it. We made this collection in 2020, put it out publicly so other people could look at it, and have been sort of churning away at it since. And that leads to our year 1 collection where we got about 40 hours of flight data. Now, I can't really emphasize how nice it is to have a 40-hour flight data test set, considering that equivalent data sets that we've seen from like Oxford with their walking data set or a couple of drone-based collections rarely get past about 5 or 10 hours of like good, usable, well-collated tabular data. Whereas here we have fully time-aligned, fully synchronized, well-constructed data at about a 10 hertz sample rate, which is surprisingly nice. And all of this was collected over Ottawa, Canada, in 2 very well-mapped regions. Well, we took that, we churned along, we got that 17-meter number, we were happy, but then we sort of went, well, we're over land, who really cares about this? I mean, you could use visual navigation and get to 5 meters, which has also been done. So we did something silly. We decided to go fly over water. And fly over some of the Great Lakes, which are particularly deep for water as well. And we're still working on this data, but we're seeing very similar results over those cases where you can demonstrably show that those other LP&T technologies wouldn't work. Again, all of this publicly available, both on the Zenodo page that houses the first-year website, as well as through our repository through our package MagNav.jl. You can just pull it in, use it, churn away, do whatever you'd like. So all in all, we've got about 80 hours of flight data, fully kitted up Cessna. This is great. If you want to navigate off the tail stinger, you can do that. Learn how to navigate. It's a good old time. However, if you want to start addressing the problem of platform calibration, you start looking at the magnetometers within the cabin itself. And what we've kind of noticed over the years of collection and working with this is that mags 4 and 5, so the ones towards the back of the plane, are what we like to call our easier ones. Mag 5 is very easy. There's very few electrical signals within the plane that go near it. It's on the roof of the cabin at the back of the cabin. Mag 4 is directly below it on the floor, which has some control signals for like the rear rudder as well as some of the lights back there. And then we have our medium or kind of hard magnetometer with magnetometer 3, which is on the fuel pump, which is where it turns out those voltage and current sensors end up being extremely useful because you can directly just pull that in and say, this is what the fuel pump is doing. This is the electrical environment there. We can now use that for compensation. And Mag 2 is on the back of the pilot and half unusable because of radios. But using all of this, you can get a pretty good view of what's going on, and that kind of led into this challenge problem that we put together, and we've done for the last several years with sort of rolling admissions, where we ask you to take sort of the minimum number of magnetometers and supplemental sensors that you can, and try to replicate the tail stinger from within using exclusively information from within the cabin. If you want to see more of that, we've got our challenge problem website at the bottom, and I'll pull these links up again at the end. So to sort of set ourselves up for real time, though, we have to look at offline first. So we've got data, we've got a basic idea of the problem. Now, how do you actually put these two things together and do MagNav sort of on your laptop? We're not in the plane yet. We're still operating in a fully offline fashion. So that's where we came up with last year's topic, which was sort of this knowledge-informed AI infrastructure for magnetic navigation. The core idea is we already know quite a bit about magnetic platform compensation. We know kind of what we need to be looking for, what we need to compute, how we can apply it, and how we can actually take this compensation and get to a navigable signal. So as we did that, we sort of started cleaning up our documentation and trying to make it a bit more clear for everyone else, because when you've stared at a problem for 3 years, you tend to sort of get in your own head. And in the process, we came up with a couple of good ways to explain it, which is that we're really sort of doing a SciML-style approach, where we've got this physical model, this pseudo-simulation of what the magnetic environment should look like with Tolles-Lawson, which is directly based off of trying to compute and determine the eddy currents, the induced fields, and the permanent fields within the plane in a very static fashion. It knows it in regards to attitude and elevation. It does not know it in regards to time. And then we augment that with a neural network trained off of some of the magnetometer readings and some of the supplemental data to actually build out what the transient inferred correction is. So we're not fundamentally building a whole new compensation framework. We're augmenting the currently existing one to sort of make it apply to what we need it to do. And that's to deal with things like radar, cargo, personnel. I mean, we have a whole example on our package that actually walks through how you can detect the direct impacts of a particular strobe light on one of these magnetometers. And it turns out that since the neural network doesn't have to learn about the modeled components, you can get away with a 2 or 3 layer just feed-forward network. It doesn't need to be anything too powerful. But that very small network ends up being just about perfect here, and it's helped us avoid what's happened for some of the pure machine learning approaches, where you end up with a 20 or 30-hour training set, a very large RNN, or a couple of transformers, and then it doesn't really transfer well. Because you've trained on 30 hours on one plane, then you go to a different plane of the same make and model, and it doesn't really work because there's a couple of other particulars there. Whereas in our case, with a small 2 to 5 minute transfer function, or if you're training from scratch, about 20 minutes, so just during takeoff proceedings, retrain the network, and then you're good to go.
So should we do that for the neural network for each airplane?
Yes and no. So it depends on what you're saying. Yes. So he asked if we're training a new neural network for each new airplane. I hate to say it depends, because by airplane here, you can mean same make and model. So we're talking about all of the Boeing 737s, or we're talking about each particular Boeing 737. In this case, we've looked at what we called a sort of a group model. So all of the 737s, and you can get to decent performance. You do still want to potentially fine-tune or retrain during your takeoff or initial flight, because you want to deal with some of the oddities of that plane. Because sort of some of what I've discovered with a lot of the work on this is that no two aircraft, even if it's the same make and model, are the same. They'll have different software blocks, so they'll be running different interpretations of their own sort of way to manipulate the circuitry, or they'll have different damage they've undergone, different maintenance procedures. You're going to need to fine-tune for any new sort of tail number that you're hopping on. I hope that answered your question. And sort of what I was talking about earlier, this is what it looks like when you blow up that previous diagram into what we're actually doing. So you take Tolles-Lawson, you keep it in the vector form, break it out into its individual components, and then you use just this neural network here to build a small additive correction, and you move on with your life. This turns out to be extremely powerful and tends to just work fairly well on its own. As you can sort of see here, where with the individual components, our correction doesn't have to be that big. Tolles-Lawson will buy you a lot, especially on a geosurvey aircraft with a sufficiently well-placed magnetometer. But without it, we're dealing with sort of magnetic field errors in the area of 130 to 150 nanoteslas, which is still sort of beyond the bounds of what you can navigate off of. Your error is larger than the actual signal you're trying to use. Once you add in sort of if you just go to a straight up vanilla neural network, just use an RNN, you can get to the 60s, which gets you a pretty good navigation, but it doesn't really transfer well. It doesn't really extrapolate well either. And then when you combine the approaches, so Tolles-Lawson and the neural network, in some cases, you do as poorly as 55 nanoteslas. I say you do as poorly as 55 because that's the number we put here because it's sort of the largest magnetic field error that we've seen when you have a well-constructed model. I've built models using this technique that have gotten as low as 9 or 10 nanoteslas, which is eminently navigable. At this point, you're the same as the day-night cycle, and we no longer care. And this has already been released and integrated into MagNav.jl, is extremely well documented, and has several Pluto notebooks that can walk you from, I just looked at the data, to I'd like to navigate. So that's sort of offline navigation. We're, at this point, still existing purely in the realm of, if I just handed you the repository and said, have fun, you could probably get here in about an hour. Now we're at real time. Here we have other problems. Here we no longer have all of our data already ingested, already having gone through the communication systems and already arrived at your laptop fully time synchronized and ready to go. We now have to deal with sample rates. We now have to deal with things like different connection standards. We have to deal with data being synchronized almost, so things potentially arriving out of order. We have to deal with things like altitude variation. There's a lot of other things that show up when you actually try to deploy this versus when you just run it on your computer and take a look. And sort of a lot of this boils down to just really dealing with and digging down into that communication system, where we end up using LCM, so the Lightweight Communication and Marshalling Standard, because as we've kind of found, it's exceptionally common in the aerospace industry, especially in the tooling industry, for people to use these very lightweight communication protocols to try and communicate. Now, of course, using this, you're not going to get everything that we have in the offline dataset in that full tabular system. You're going to get the inertial system, both in a processed and unprocessed form. You're going to get GPS, so you know where you are for sure. You have a truth signal of some kind. You'll get the magnetometer, because we directly attached an Ethernet cable. And that's about it. So all those nice, lovely voltage and current sensors we had, we don't really have in the real-time environment. So we kind of have to lean much more heavily on things like more precise attitude estimation, more precise calibration, and really lean on sort of understanding what we knew before to identify other signals that we should bring in. Oh, there we go. So at this point, actually, I'm going to pop out of the slides because things are actually running. If I can get the dashboard to come up. Aha. It's not really fair to say I'm running things in real time and then just show you a whole bunch of pre-made GIFs, a whole bunch of pre-made tabulatures and everything else that just says, yeah, we did it in real time. It's a lot more fun to actually do it in real time. So here, in this terminal window over here, which can anyone read that other than me? Okay, well that's good at least. This breaks out all of the individual inertial fields, GPS fields, and sort of what you would need from the magnetometer itself to start feeding into the algorithm. This Mackie screen that I have up here is put together by sort of our processor, which acts as a full ingest. So this isn't truly real-time in that we're not on a plane, but I am taking a recorded segment of flight and debouncing it to act like those messages are coming in 5 times faster than real-time because we only have 5-ish minutes. And I'll hit go, and then pop back over here. So at this point, thank you. At this point, it's loaded in the actual model. It's looking at sort of ingesting a good initial EKF state because we're using an extended Kalman filter to build a corrective navigation signal. And then once it gets that, you'll start to see these individual charts start to populate. In fact, you've already seen positions start to populate. It is a little goofy because this is an algorithm designed to run at real time, and we are currently running at 5 times real time. So you'll see some fun start to show up when you realize that it thinks the plane's moving about 5 times as fast as it is. But what you can quickly see is that after an initialization period, sort of once you get past this area of low magnetic variability and start to hit components of the map where you're getting a good magnetic variation, the MagNav signal very quickly starts to converge onto the inertial signal for quality and eventually surpasses it because it's no longer drifting as hard as long as you have a good compensation. Now, as I'd sort of alluded to before, we don't have every field that we'd like to have, so our compensation is worse than we'd like it to be. In training and evaluation on this flight leg, when we have the full the full suite of fields that we normally use, we see a compensation error somewhere in the area of like 22 nanoteslas, which is very good. But when we're actually doing the real-time replay, we're somewhere in the neighborhood of 50 to 60 nanoteslas because we lose some of the current sensors and timing. And timing issues start to become a problem. But I'll have to zoom in here on the nav error. As you can already see, with MagNav, we've beaten an exceptionally well-calibrated INS system. We've locked on our confidence ellipse at a good point. Our position errors are very stable, and we're looking at about somewhere in the neighborhood of like 30 meters right now. And by the end of this replay, I think it gets to about 45 meters of navigation accuracy. Now, of course, I say it'll get to 45. It's still a stochastic process, given it's a Kalman filter. So if it does better, oh, no, it's not going to do better than I thought it was. It's going to do about as well as I thought it was going to do. But really the important thing here is so long as you have a stable calibration, which you can pretty quickly get to with MagNav.jl, you can then leverage that with some simple other Julia libraries for message streaming, as well as some of the asynchronous systems within Julia to get to this point where you can do real-time MagNav, and I can honestly, actually personally say that I've taken this same set of software, and instead of replaying messages, actually hooking it up to a router so it's getting the correct messages from the rest of the hardware, and you can run it mid-flight now. It's not very difficult to sort of change this back over. You really just have to turn the other script off. But you can see very similar navigation errors mid-flight. And there's actually a few companies that we've been working with that are currently trying to get to that point for commercial aviation as well as other things. I think, yeah, I'll stop the replay. Actually, I'll just let it go. I guess at this point, I'll pop back to slides, if slides will come back, and then I'll just sort of ask for any questions, because if it'll let me. Yeah. So, and here I've got our project codebase for MagNav.jl. It's also just perfectly available in the package manager. We've got a Docker that has everything instantiated, including the Sanders geophysics data, so the year 1 data, I believe. We have a Dataset over on Zenodo, and we've got our challenge problem description available for everyone as well. Thank you. Any questions?
Thanks, Jonathan. Yeah, what are your questions?
Thank you very much for a wonderful presentation. Why Julia and not any other software here?
So there's a couple of good reasons for that. Initially, it was because we were trying to build out a simulation system for estimating the magnetic environment within the plane. So Julia was very convenient because we were going to be able to differentiate through sort of our mathematical model of the plane itself. Since then, we found a lot of other computational efficiencies, namely the ease of ability to write sort of your model once and deploy it on a wide variety of architectures. So we've had this running on embedded hardware like a Raspberry Pi up to a supercomputing cluster that has multiple GPUs. So initially, because of some niceties with the auto differentiation system, now because it runs everywhere and I don't really have to think too hard about how I rewrite all of this in Torch such that it can run on both the CPU and the GPU, and I'm not using special functions, and it's just a lot easier. And I do say that going, I'm primarily a Python developer, so I'm not saying that because it's because I know Julia. I know Python much better. It's just a lot easier to do things like this in Julia than it is in Python because of some of the niceties around, especially Flux. Flux and Lux have been beautiful.
If I may ask, do you a lot of the development by yourself? Or
So
how large is your team?
our team is, I can pull it up to here. Really, for the last 2 years or so, it's been these 4 people. So myself, a PhD, well, he's graduated now and then was a postdoc at the Julia Lab, Albert Gnadt, Alan Wolver, and Glenn Carl. So a couple of my colleagues, as well as Albert Gnadt, have done the majority of the work, including myself. Most of what I've done has been on the real-time translation, project management, which is always great with grants, and then a lot of work early on with helping trying to formulate some of the individual ideas and making sure that we could actually get things working. Cool. Oh.
So did you ever try just running a Kalman filter without your approach to see
Yes.
how it does?
If you run a Kalman filter off of just the inertial navigation system, you're going to see identical results. So when you get to, where are we? Here, if I get, actually, I can just do this. So this blue line you see here is just a Kalman filter running purely off of the inertial navigation values. If you run it off of that plus MagNav, it drifts into infinity very, very quickly because you've introduced functionally random noise as a truth signal. You kind of have to do some form of compensation.
I see, yeah.
So Tolles-Lawson initially, and even then you'll see degradation in sort of navigation relative to our approach because you still have quite a lot of noise. You do really need to get that compensation error under about 100 to see something useful, 50 to see something okay, 10 to see something that's a GPS replacement. Cool.
Okay, so it's thought as an GPS replacement or as an addition to GPS?
It is in addition to GPS. This is not going to get you to GPS's aviation promise of 5-meter accuracy. You probably don't need it. Your plane's bigger than 5 meters, but that's what GPS is able to do, especially in its currently deployed form. However, GPS is very easy to jam, whereas this is all internal to whatever vehicle you're flying it on. So even if this only gets you to 50-meter accuracy, at least from what I've seen, for 95% of use cases, that is more than good enough for what people are actually trying to do with GPS.
Okay, thanks to the speaker again.